Hello, this is Professor Kuehn, and welcome back to my lectures on Einstein's theory of relativity. You might recall that in my last lecture I talked about how light can exert a force on an object that it strikes, and this seems to imply that light acts as if it has some mass, which is perhaps controversial. You've probably heard that light is a massless object. So how is it that light acts like it has mass? Well, the solution, according to Einstein's theory of relativity, is that energy and mass are in some sense equivalent. So what I'd like to do in this lecture is talk a bit more about relativistic energy and momentum. And let me begin by describing a thought experiment in order to highlight this equivalence between energy and mass. So the subject is relativistic momentum, mass, and energy. And I'd like you to begin by considering a rather mundane example where one has, let's suppose, a train car. And on one end of the train car, I know this is once again a contrived example, but that's the nature of these examples because I'm trying to highlight some specific feature. So let's suppose that there's a bullet, maybe a big cannonball in the cannon on one side of this train car. And if you think about the mass of the entire train car plus the mass of this ball right here, it makes it so that the center of gravity of this entire system is not exactly in the middle of the train car, but maybe a little bit off to the left. Because after all, that cannonball has some mass. So this is the position of the center of gravity, or the center of mass, of the cannonball and train system. Okay? Now here's what I want you to imagine. I want you to imagine that this cannonball is fired, and when it's fired, of course, there's a bit of a recoil. That is, the train starts moving to the left. Now, of course, the train is much heavier than the cannonball, so while the cannonball has an enormous velocity to the right, the train might have a very small velocity to the left. Nonetheless, it does move a little bit to the left. The cannonball, of course, is flying toward the right, like this, but because this is a closed system, you might say, that is, there are no external forces acting on this system, the center of gravity of this system remains in the exact same position. That's because as the train is moving leftward, the ball is moving rightward, and those conspire in such a way that the center of gravity remains in the same spot. And then a moment later, what happens is the cannonball strikes the opposite wall, and the train comes to a stop as a result of that, with the cannonball lodged in this wall right here. I guess maybe to be consistent, I should still draw the cannon over here and the cannon over here. But this entire thing has now come to a rest, and once again, I just want to highlight that the center of gravity, or the center of mass, of this ball train system has not moved. In other words, the center of mass is stationary throughout this entire process because there are no external forces acting on this. And maybe I'll just highlight once again that the transfer of mass, of the mass of the bullet or the cannonball, from left to right, and the shifting of the train from right to left make it so that the center of mass is stationary. So it's just kind of explaining maybe in more detail what happened here. Okay, there's nothing really that controversial about anything I've said so far. But now I'd like you to consider a slightly different situation. We have the exact same train, like this, but now instead of a cannon on the left-hand side, I want you to imagine that there's a flashlight on the left-hand side. So here's a flashlight. And once again, we have this center of gravity, or center of mass, of this train and flashlight system that's somewhere about in the middle of it, like that. And now let's suppose that the flashlight suddenly turns on, and as a result of turning on, as we mentioned before, remember light has momentum. And as a result, because it's got momentum moving to the right, that means that the train, once again, suffers a recoil and moves a little bit to the left. So it starts moving to the left, just like when the cannonball was fired. Of course, it's going to be a very minuscule effect, but nonetheless, it does start moving to the left just a bit. Okay? And this light flash is moving to the right. Okay? Now, I want you to think about a moment later when, let me just still draw the flashlight here. Okay, this is the flashlight. And then a moment later, of course, the train has shifted a little bit to the left, and the light has struck the wall. Okay, so there's a recoil in this phase, just like there had been a recoil in this phase. But now the light is absorbed by the wall. Light is absorbed. Maybe it's a black wall or a black curtain over there so that it absorbs it. Light is absorbed by the right wall. And when it does so, the train comes to a stop. And the train has shifted, as I mentioned, leftward. Okay, so the train shifted leftward. Now, notice that there are no external forces acting on this system. So once again, we must surmise that the center of gravity has remained unchanged. That is, it's at the center of this train. It's in the same location. But if the train is shifted to the left, how can we account for the fact that the center of gravity or the center of mass is at the exact same location? Because after all, the mass of the train hasn't changed, but it's the mass of the train, or the train itself, has moved leftward. So how can we understand this? So here's my question. How can we account for the center of mass remaining stationary? After all, it seems like it has shifted to the left. You know, in the case of the cannonball, we can kind of make sense of this because the cannonball is now lodged over here on the right-hand side. So while the train has shifted to the left, the cannonball is on the right. But it's not like the light is somehow still there, embedded in this wall, is it? Well, from the theory of relativity, this is how we would approach this question. And this leads us, once again, to the equivalence of energy and mass, or Einstein's famous E equals mc squared formula. This is the solution to this question posed by this answer to this question that is presented by the theory of relativity. How do we understand this? Well, when the light strikes the wall on the right-hand side, it causes the atoms in the wall to heat up just a little bit. And heat is a form of energy, and energy and mass are equivalent, so insofar as this wall becomes heated up, it behaves as if it has more mass, because there's energy that has been transferred from the left-hand side, which was being stored originally as chemical energy in the batteries of the flashlight. Then that energy ends up on the right-hand side as heat energy in that wall. And this is the solution that the theory of relativity presents. In other words, we have, I'll say this once again, we had originally chemical energy stored in the battery. And then in the second frame right here, we have light energy, or energy associated with the light wave. And then finally, we have heat energy. So energy has been transmitted from the left-hand side to the right-hand side. So throughout this process, there is a transfer of energy, which is, again, equivalent to mass from the left to the right of the train. So while the train itself has moved from right to left, the energy has moved from left to right so as to keep the center of mass stationary. Okay. What I want to do in my next lecture is, I've been presenting this schematic view of the equivalence of energy and mass, I want to look a little bit more carefully at some of the formulas that appear in Einstein's theory of relativity and make a comparison and contrast of those formulas with the ones to which we're accustomed from Newton's theory.